All right, so we want to make a mold of what the tooth looks like. So you need a mold because you need to pour that mold into stone, and then the laboratory is going to use that stone cast to then fabricate your crown off of. So really what we want is we want to replicate what's in the mouth with a stone cast. So a dental impression is a negative imprint of an oral structure used to produce a positive replica of the structure to be used as a permanent record or in the production of a dental restoration or prosthesis. So if we want to get down to the next level, an impression is a negative likeness or copy in reverse of the surface of an object, an imprint of the teeth and adjacent structures for use in dentistry. So we have a few things that we want to look for that makes for a good impression material. So sufficiently fluid to adapt to oral tissues. Right? What's the point that we're trying to get across here? Sufficiently fluid. To get the details. Yeah. So if we have, remember when you guys use the light body material, the aqua color versus the purple, which one flowed or was more fluid? The light body. And the light body we want to flow because it can get in all the little nooks and crannies and into the sulcus. So the more fluid-like it is, the more readily it is to get into these little features of the preparation or in the sulcus. So we want something sufficiently fluid to adapt to oral tissues. So we need to be viscous enough to be contained in a tray. So this is important too, right? Because you don't want your patient to be swallowing that PVS. And maybe if we have extra time, we'll show you some really good impressions of material down, basically like capturing their uvula. So, right, so you don't want to use all light body, you know, most of the time. Sometimes there's indications for it, but if you use the whole tray of light body, what's that going to do? Well, when you seed it, sometimes it'll kind of, it flows too much, or not enough of it stays in your tray. So it's able to set to a rubbery or rigid consistency in 7 minutes or less. So this point is you want the patient to be comfortable. You know, you don't want them standing around for half an hour for this thing to set. And it's got to be dimensionally stable enough to allow for one or more pourings. So after we remove it from the mouth and we let it sit for a while, how much of that material is going to distort over time? So the PVS material is very dimensionally stable over a long period of time. You can let that thing sit for weeks, even months, and you'll get something, your cast that's made out of it will look very similar. With Alginate, what do you think the dimensional stability of that is? 4, right? And it's poor because it's water-based. It's a hydrocolloid. Okay? Whereas a PVS is a polyvinyl siloxane. Okay? It's an elastomeric polymer that is dimensionally stable over a long period of time. It's got to be biocompatible. Obviously, you don't want to harm the patient anyway. It's got to be compatible to their oral tissue. And at some point, it's got to be somewhat cost-effective. Although we learned at school pricing, each one of those cartridges is about $10 to us. So let's pretend you got a $10 bill on one of those cartridges, just to visualize how much it costs. Whereas Alginate, it's maybe like a dime or something. Okay. All right. So what material is used? We're going to use an elastomeric material. Okay, so we'll go through some. This is a chart taken, not directly, but Dr. Kramer had the exact same classification. I know you guys all remember Dr. Kramer's class. So elastic versus non-elastic. How would we define elasticity? When we say something's elastic, what do we mean?
Recoil in its original position.
Okay, so it can return back to its original kind of form, right? So the property, it's like a rubber band, right? So you stretch it, it'll fully recover to its original shape. So we'll say that there's no so something that's 100% elastic will have no plastic deformation, right? It always returns back. So something that's non-elastic, another word is plastic, once you deform it and you stress it, there's going to be some dimensional strain to it, okay, or a change in the length of the material. Yeah. So elastic, you guys can't really see that now. Plaster, compound, waxes, zinc oxide, eugenol are a few non-elastic impression materials that we'll use. Hardly any of them are used clinically anymore except for compound. For the purposes of this class, you probably need to know that wax is a non-elastic material because we use wax as a wax pattern to fabricate our crown. And remember what we talked about yesterday. If you have an undercut in your prep, and then you dip that dye into the wax, remember that's how we start a wax pattern. At some point, we need to remove the wax pattern from the dye so we can invest and cast it. So if wax is a non-elastic material, what happens to the wax when we try to pull it off? It'll permanently deform. And that's not good because then we can't make a crown that's accurate to their mouth. So if it'll further classify materials in the elastic category, we have aqueous hydrocolloid and non-aqueous elastomers. So what is an example of an aqueous hydrocolloid? Answers are all in there. I don't know why you ask you guys. All right. Alginate and agar. So one is reversible. The other is irreversible. So the ones that we use is going to be an irreversible hydrocolloid, which is alginate, meaning once it sets, you can't reuse that material. We have another material, agar, and we use that to duplicate casts in the lab. And that material can kind of be melted down and reused again. So we call that a reversible hydrocolloid. Both of them are water-based, and they form, it's a gel-sol reaction. So if you go back to your dental materials slides from first year, Dr. Kramer has a little segment on that that you should probably know about cross-linking gel to sol reaction. All right, so let's talk about our non-aqueous elastomeric impressions. We have 3 of them that we'll talk about in dentistry: polysulfide, polyether, and polyvinyl siloxane. We'll ignore the first 2 just for today, and we'll talk about polyvinyl siloxane. And polyvinyl siloxane comes in 2 forms. One is condensation, the other is addition. So the difference is, as polysulfide kind of polyvinyl siloxane, as that polymerizes, right, as the chains start to link up, in the condensation type, it releases a byproduct. So that byproduct is ethanol. And then the addition, there is no byproduct. So all the chains link up, and then nothing else kind of is a product of that reaction. So which do you think would be more accurate and better to use inside a patient's mouth? Addition, because it should be more stable because there's no byproduct as it's setting, right? So it should be more dimensionally stable. So the one that we'll use in the mouth, the ones that you have used in clinic so far, in sim clinic, has been additional PVS. The condensation you've used, I believe already, did you guys make the little putty index for your class 4 restorations, right? You had 2 little things, 2 wads of putty, and then you mix them together. Okay. So we can use those as a template to kind of set in the mouth, but those aren't to be used to make a final impression, to make a prosthesis kind of off of. And the reason for that is over time, because of the condensation, is not as dimensionally stable as our addition PVS. So condensation has a byproduct, which is ethanol, addition does not. Okay, so we talk about elastic and plastic deformation. So this is a stress-strain curve. The way to read these is strain is, think of it as the change in distance, and stress is how much force you apply. So at some point, as we go along the x-axis, or let's go along the y first, we go up in the y-axis as we push harder on a material. As we push hard, okay, the thing will start to flex. So think of a plastic fork, right? You got a fork, and you take your finger and you start pushing. So you can measure the stress, how much force you apply, and then on the x-axis, strain is how far it moves. So a plastic fork will move, and then when you let go of it, it'll go back to its original shape, or at least close to it. So that's a pretty elastic material. So what if we had a metal fork and we start pushing on it? How would the slope of that stress-strain curve change? Would it be steeper, or would it be more shallow? Remember, y is the stress, x is the strain. Okay, it would take more, say again? Steeper slope, so it would go this way. Yeah, okay? So to move the same amount of distance, you got to push harder. So if you were to draw that line, it would go at a steeper angle, okay? So stress, strain curve, plastic and elastic, okay? And our materials that we're using for our impression materials is sort of, will have both properties to some extent. Okay, we actually call it a viscoelastic material, which we'll get to in a later slide. So elastic strain, deformation that is recovered upon removal of the externally applied force or pressure. And plastic strain is deformation that is not recoverable when the externally applied force is removed. All right, polyvinyl siloxane. Cross-leaking occurs in the presence of a platinum catalyst with no byproduct. So there's a little chemistry here. So we have two things that we're going to talk about in terms of time: working time and setting time. So the total time from the start of mixing to the final time at which an impression can be fully seated without distortion is what we call the working time. So when you are injecting your light body onto the teeth, and then you have your partner loading the tray, you guys have to work within this working time. So you need to ensure that your tray with the medium body is seated within this time frame. Because if you wait too long, then that material in the tray starts to set up already, or the material in the mouth starts to set up already, and you're going to have some distortion as you seat the tray. And the other thing about PPS is, as within this working time, if you have the two touch each other, they all polymerize together. So it'll feel like one material. You can't distinguish, other than the color, the junction between the light body and the medium body. So you'll find if you take a little bit too much time, right, and one material starts to set before the other, as you remove the impression and you analyze it, you'll see the two materials separate because it has already started to set up. Okay? So you got to work within this working time. So on the cartridge that you have, it'll have a working and a setting time on there. So I believe it's 2 minutes, 2.5 minutes, something like that. So as you make your impressions in Sim Clinic, also in the clinic downstairs, what you'll need to do is kind of practice, or one of the skill sets you'll need to develop is, you're essentially the quarterback of this whole operation. Right? You got a assistant or a classmate that's helping you load the tray. You got to figure out how quickly you can inject onto the teeth, and you kind of got to figure out how strong their forearm muscles are and how fast they can pump that gun, because you kind of want to time it so that the minute you're done, the tray is ready and ready to seat. Okay? You don't want to have that light body sitting on the teeth too long, then you're sitting there waiting for your classmate to load the tray, because the stuff in the mouth will set faster. Why does it set faster in the mouth? Because it's warmer. It's in the oral environment. And then the set time is the elapsed time from the start of mixing until the impression material becomes firm enough to resist permanent deformation. For an elastic material, it represents the time at which the impression can be withdrawn in the mouth. And for the Aquasil PVS that we use, that's going to be 5 minutes. So the PVS in the clinic will have an extra light, I think V is what, volume, something like that? Viscosity, sorry, volume. Extra light viscosity, that's this one. We have a light viscosity and a heavy, or a medium and a heavy. So lighter viscosity allows for the material to flow easily into the sulcus and to capture the surface, capture the fine surface detail of the preparation. And a heavier viscosity provides for adequate rigidity to prevent distortion and to minimize deformation. So you got a heavier material in the tray so that once it sets, it's much more rigid. So when you're going to pull it out, it'll return. It'll be easier to return back to its original form. And the other reason for using a heavier viscosity material is because it tends to flow less. So when you're seating in the mouth, it won't flow down the back of their throat. Okay, good with that? Viscoelasticity is a property of a material that it exhibits both viscous and elastic characteristics when undergoing deformation. Viscous materials like honey resist shear flow and strain linearly with time when a stress is applied. So an elastic material strains when stretched and quickly returns to the original state once the stress is removed. And a viscoelastic material have elements of both of these properties, as such exhibiting a time-dependent strain. So I am going to nerd out on you guys and show you guys a 2.5-minute video on viscoelasticity. It's about strings and Dashpot. I think it's fascinating, but not everybody thinks like me. Any engineers in the room? Anybody graduated as an engineer? Nobody this year? How about chemistry majors? Are there any chemistry majors? All right. Okay. So viscoelasticity. You don't understand this. It's probably from the 70s, but I think it explains viscoelasticity so well.
Method of understanding a polymer's behavior is the spring and Dashpot model. The spring represents the elastic behavior of the polymer. The elastic portion of the model acts as a metal and has fully recoverable strain. The Dashpot represents the viscous behavior of the polymer. The viscous portion of the model acts as a fluid and has unrecoverable strain. One way to understand the spring and Dashpot model is by examining the behavior of the system with.
So the Dashpot. So have you guys seen? I don't know if those doors. That one's probably broken. You see the little door stopper thing, right? So when you close the door, what happens? It doesn't just slam shut, right? So it's got a Dashpot-like mechanism in there where it's a time-dependent strain. So it closes slowly over time. It's not sort of an immediate kind of closure. And that's essentially what that is. Think of it also as a syringe, right? You got, a little needle, and then you're trying to withdraw or draw kind of air, let's say. You know how it's kind of resistant to that. So it's a time-dependent strain is sort of the idea of what a Dashpot is. And a spring, I think you guys are all familiar with.
The suspended load. A graph of deformation and time helps you understand the mechanics of the system. The first component of the model is a spring. When a weight is added to the spring, an immediate deformation is observed. When the weight is removed, all of the elastic deformation is recovered. The second portion of the model involves a spring and Dashpot in parallel. The spring portion of the system cannot immediately deform because the viscous component slows it down. Therefore, the deformation takes place over a period of time. As the weight is removed from the system, the deformation recovery of the spring is slowed by the Dashpot. The third component of the model is the dashpot. The dashpot flows while the weight is applied to the system. When the weight is removed from the system, none of the viscous component is recovered. To fully understand the model, the three components must be superimposed. When the weight is applied, the system undergoes an immediate deformation due to the spring component. The second component, with the spring and dashpot in parallel, produces a deformation over time. The viscous deformation of the third component is added to the second component. This results in a model of the behavior of the loaded system over time. When the load is removed, the initial deformation of the spring is recovered. Then the deformation of the spring and dashpot is recovered over time. The deformation of the dashpot is never recovered. The result is a permanent deformation of the system.
Hello and welcome to topic 4 in May.
Okay, so I know not all of you are enthralled with this topic, or it brings back very bad memories. So what do you guys actually need to know about viscoelasticity? Do I need you to understand all the graphs in the spring and dashpot? No. But the idea is that PVS is a material that is both viscous and elastic. So what I need you guys to know about PVS is that it's time-dependent strain. So the idea is, yes, it'll flex back because it's an elastomeric impression, or it's an elastomeric material, but it's also viscous in the sense that the faster you remove the impression, the less it distorts. Remember, it's time-dependent. So the less time it takes for you to kind of remove and have that impression material flex over the undercuts and then recover, then the less plastic deformation occurs. So with PVS, it generally returns back pretty well, you know, even if you kind of go a little slow. But Alginate, definitely, we teach you, in really all impressions, you want to remove it using a kind of snapping motion. So you don't want to sit there and kind of struggle and kind of loosen, loosen, loosen. Sometimes you have to just because of the amount of undercuts. But just a principle you need to understand is the faster you remove the impression, the less it distorts. Thixotropic. Geez, another big word. A time-dependent shearing thinning property. Certain gels or fluids that are thick or viscous under static conditions will flow or become less thin or less viscous over time when shaken, agitated, or otherwise stressed. So it's a time-dependent viscosity. So again, something else that is time-dependent. And this is an even shorter video that some like 12-year-old kid put together, but I think it works out okay.
Hi, it's Wolf Experiments here. I'm going to be showing you how to make thixotropic fluid. Now, what it is, it's a solid and a liquid. So, as you can see, I can, if I want, pick it up, leave it for a little while, and it becomes a liquid. Okay, so...
Okay, thixotropic, right? So, in its resting state, right, feels a little thicker, it doesn't really flow. When you pick it up, now gravity is acting upon the material, so it's been shaken, agitated, or otherwise stressed. It'll change its material properties. So PVS, or the polyvinyl siloxane, isn't quite as thixotropic as the material that kid showed, right? But it has some thixotropic properties. So if you notice, as you load the tray, with the medium body, it kind of tends to sit there. But the minute you agitate or kind of stress it, it'll have some flow properties. Right? So when we're helping you guys kind of seat the tray, there's times where I tell you, okay, give it a little wiggle, right? You do a little dance, you celebrate if you've wiggled enough. So the idea is that as you go in, right, you can seat it straight up, or if you just give it a slight little wiggle, you've agitated or stressed it, so it'll tend to flow a little better. Okay. So the other application to this too is, you'll see in the videos that we'll inject a light body impression material into the sulcus, and if you want things to spread out a bit, you want to use, sometimes you'll see the practitioner blow a little air around it to just kind of spread it thin. So again, once you've shaken or agitated, it tends to improve sort of the flow properties to get it exactly where you want. So the main point of this is stressing the material allows it to flow better. All right, so let's talk about retraction cordon. We touched upon this. Two reasons for it. One is for hemostasis and for fluid control. So you have bleeding that occurs sometimes around the soft tissue. And then fluid control, you have that gingival curricular fluid that likes to kind of flow up. So retraction cord will help kind of keep that down. You also want to create space for impression material to flow into the sulcus. So you want to push the tissue. It's usually going to push it out, and also it'll push it a little bit apically. Okay. So you tend to see after, let's say you've prepped your margin exactly equigingival, equal to the gum line. As you place cord, sometimes you'll see it not only move out, but your margin will be a little bit more exposed too. So what we'll teach you guys is a 2-chord technique. You have a bottom chord that's smaller and a top chord that's generally larger. So the bottom chord is there to control heme. You want to cut it to the exact circumference of the tooth. So you don't want, you want the end or the beginning to meet the end. So what you'll do is start packing, and as you get close to the end, you'll just trim that up. Right? So you pack one around the tooth. So typically a size 000 or 0. So the more zeros you have, the smaller. 2 is sort of the largest chord that we'll have. Okay. Top chord will be larger, and the purpose of that is to create space. So this is the chord that's going to help push the tissue out. You want to leave a little tail for ease of removal. So what's going to happen is you're going to remove that top chord before you inject the material into the sulcus. And typically size 0 or greater, where the idea is just get the biggest cord you can in there without really having to damage the tissue. And these cords are typically soaked in a hemostatic agent. Talk about that next. So hemostatic agent, we have Hemodent and Viscostat Clear. So those are the two kind of brand names that we have, and it's a 25% aluminum chloride solution. So you take the cord, you have it soaked into this solution, and it functions as a vasoconstrictor, so it helps minimize bleeding. We also have ferric sulfate. The brand name would be Viscostat. Don't confuse that with Viscostat Clear. And it coagulates blood. It can affect the setting time of some addition of silicones and can stain the gingival tissue. So we tend to use this a little bit less. So I would recommend using Hemodent or a Viscostat Clear, which is our aluminum chloride material. So the idea is that you take a little cord, you put it in the solution, it kind of soaks it up, and then you pack that cord into the sulcus. Okay, so we talked about all of the impression material we're going to make on our prep. But for the opposing arch, we're generally going to use Alginate. So it's irreversible hydrocolloid. Chemistry of hydrocolloid is based on sol gelation, or large water-soluble polymer chains cross-linked to form a stiff gel. It's got pore fine detail reproduction, but it's adequate for removable prosthesis and laboratory duplication purposes. It's also good enough for our opposing tooth, the one that we're going to make the crown against, in terms of knowing how to contour the tooth so that the occlusion is in kind of balance, or you got equal contacts everywhere. So if you don't pour it up right away, you should store it in 100% humidity. Don't just dunk it in water. But what we'll teach you is to wrap that in a wet paper towel, put that in a Ziploc bag, and then I'll buy you some time so it prevents distortion. So the general rule is once you take it, pour it right away. Okay. If you can't do it right away, wrap paper towel, put it in a Ziploc bag. That'll buy you some time. If you're 2 hours out, probably a little too long. Okay. Yeah, let's just wrap this up, and then we'll show some videos. But Viscocryl, just want to touch upon this today. We're going to use integrity material as our provisional. I hope all of you guys watched the video. It's pretty clear with the steps that we're going to do. But basically, it's a dual-cure composite resin where it's paste, and it mixes, and it's chemically cured. So the advantages is the low exothermic reaction, there's low shrinkage, and it's improved aesthetics. So right now, this is the only provisional material that we've talked about. I think some of this stuff will make more sense as we compare it to other provisional materials that we'll get along to later in the course. So when we do some of the other, like polymethyl methacrylate and other provisional materials, we're going to come back and revisit this so we can compare and contrast. These will make a little bit more sense. But just know it's low exothermic reaction, meaning it doesn't damage the pulpal tissue as much when it sets. It doesn't shrink as much. And it's got improved aesthetics. The disadvantage is it's more brittle compared to other materials. It's less stain resistant, and it's limited in shades and cost. Okay. So that's kind of it for the lecture part. What we're going to do is we'll come back and I'm going to show you some videos on impression making. Hopefully we'll get you guys out of here before 9:30, maybe even a little earlier than that, so we can get in there, start prepping, and start making our provisionals. So if you guys can help too. We have just a little pre-assessment. It's like a 3-question little assessment thing to see if you guys have watched the video and read the clinic manual. So if you guys don't mind helping passing these out. So everybody gets one. Let's turn it face down. It's not for a grade. Just want to see if you guys have even watched the video. So get out pen and paper. This is one thing that you definitely don't want to cheat on. Think about risk versus reward. Don't cheat on something that you're not going to lose points over. But the risk is, man, if one of us catches you cheating, you're in a world of hurt. So face down. It'll take you about 1 minute to finish. After you finish, face down. Face down. Face down. And then after you take the quiz, turn it in, write your bench number, name, turn it in, and you guys can go on your break. And we'll give you, what, 15 minutes?
In the video, we reapplied the flow at the end.
Yeah.
Built up a little margin. Is that the same?
Face down. Face down. Face down. Face down. Face down. Okay.
In that video, when he had to readjust it after he took it out the original time, one of his margins or whatever was messed up, and he had to add flow. Was it the same thing, or was it the other thing?
Different thing.
The one we would use for filling?
Yeah. Yeah. Remember, this isn't for a grade. It's just to see how well we're teaching this course. If everybody passes, then we know we're doing a good job. If everybody fails, then we know we're doing a terrible job. All right, everybody have a sheet? All right, go ahead. It'll take you about a minute. And then turn it into one of the instructors, and we'll kind of go over this when you guys get back.